Generally, when controlling sensors or actuators with a microcontroller unit, MCU, the interfaces available include Universal Asynchronous Receiver Transmitter, UART, Inter-Integrated Circuit, I2C, Serial Peripheral Interface, SPI, and Parallel Communication. Honestly, UART, I2C, and SPI are used quite frequently, while parallel communication is often employed for controlling displays, such as LCDs. In most cases, you will see UART, I2C, or SPI being used. When it comes to sending data, I2C and SPI are quite similar. Typically, I2C and SPI allow you to read or write values related to specific registers without a complex protocol. It's a straightforward structure where you simply read the register value or write to the register. In contrast, UART can have a more complex protocol structure. In some cases, certain sensors can operate using UART, SPI, or I2C, depending on the mode settings. In such cases, it is not simply a matter of writing to the register. Instead, the same protocol must be used for writing, passing, and interpreting values across UART, SPI, and I2C, similar to how values are lost in UART. However, for now, we will use Universal Asynchronous Receiver Transmitter, UART, as the standard. We will create a protocol based on UART. So, what is a protocol? You don't need to think too complicated. Just see it as a simple agreement. The microcontroller unit, MCU, can communicate with sensors and actuators, or it can communicate with a PC or other devices, exchanging data with each other. However, it's not just about sending and receiving data randomly. It's about making agreements when sending data between the two parties. It's about establishing rules. To put it simply, you can think of it as a protocol. Therefore, depending on each sensor, each actuator, and the situation of a particular microcontroller unit, MCU, there can be various protocols. But there is no perfect protocol. In some cases, a microcontroller unit, MCU, has excellent performance, allowing it to send a large amount of data at high speeds all at once. However, in other cases, the performance of the MCU may be limited, resulting in a maximum amount of data that can be sent at one time. Therefore, there is no perfect protocol. I believe that you should create a suitable protocol tailored to your specific environment. When looking at terms related to protocols, one of the frequently mentioned terms is start of text, STX. In the case of STX, it literally means the starting character of the protocol, as indicated by the English term start of text. However, it should be understood not just as a character, but as the first byte that marks the beginning. However, generally, it is one byte. But in some companies or other cases, there are instances where 2 bytes are used, and sometimes 1 byte is used. This varies from company to company, and you can decide whether you want to use 2 bytes or 1 byte. On the other hand, there is something called ETX. It is the last character, the last byte. Similarly, it can use 1 byte or 2 bytes, and in some cases, it may only contain the start of text, STX. There is no end of text, ETX, only start of text, STX, but in some cases, STX can have a byte count of 1 byte or 2 bytes. Next, there is the checksum, which is also referred to as CRC. You can think of it simply as a check to verify whether the data sent and received is intact, not corrupted, and has arrived accurately. Therefore, it can be considered as a byte of data used for verification. This can be 1 byte, or if there is a lot of data, it can be 2 bytes. There are also various methods for generating the check byte, but I will explain that again later. Based on this, indeed, let's try to design the protocol. First, we need to create the start of text, STX, and end of text, ETX. In my case, if I search for a random number generator on Google, it immediately shows me a random number generator. In general, for cases like STX ETX, I typically use 1 byte for STX and 1 byte for ETX, which means that 1 byte can represent values from 0 to 255, from 0 to After generating 255, it suggests a number without any thought. Then I convert 41 from decimal to hexadecimal and use that. Similarly, the end of text, etext, is set in the same way. So in my case, I set the start of text, stx, to AF and the end of text, etx, to 7D in hexadecimal. Additionally, I would like to mention that the order of these elements can vary between different protocols. You can create it according to your preferences, but in my case, the next thing is related to the length, specifically the data length. Len is now talking about the data length, and I will mention more about it later. So, Len is unsure about how the data will be. Next, you need to include the CMD. For reference, I have placed the length, len, in front, but now the CMD data-related elements are coming up. And if the data length cannot be expressed in just 1 byte, then the length could be 2 bytes or 3 bytes instead of a simple 1 byte. You can adjust this according to your preferences, but for now, I will assume that the length of len does not exceed 1 byte. So I will set it to just 1 byte. As for CMD, I take into consideration what kind of data is being sent. For example, whether it is a command to control the speed of an actuator, a simple on-off command, or a command to change direction. There can be various types, so I have placed the corresponding type in the CMD area. Similarly, this could also be 2 bytes or 1 byte, because the number of types is more than 256, which cannot be simply represented in 1 byte. You can set it as you wish, but I will assume that all cases will be included within 256 possibilities and set it to 1 byte. Next, we move on to the data area. Honestly, this data part may or may not exist, so if there is no data, the next byte will just take its place without any gap. If there is data, then I will include as many as needed. Up to data 0, data 1, data 2, data 3, data 4, and data n. Instead, here it will be reflected on the length side. So, we need to consider the reflections as well, and later. In the next session, we will be discussing communication with Arduino, and I will explain it again at that time. Next, we will move on to checksums. There are various methods for checksums. A checksum can be either 1 byte or 2 bytes, but for now, let's consider it as 1 byte. Generally, I often use the XOR operation for checksums. This involves including all the data before the checksum, whether or not it is included in the checksum, and performing an XOR operation or simply adding them together. However, if you perform the addition operation with 1 byte, it will eventually overflow and keep looping. You can do it in many different ways. After you have performed the XOR operation, you might subtract it from 255, or even use other methods if you like, but you can implement it in the way you prefer. This is how you construct the protocol. As I mentioned earlier, there is no perfect protocol, and the order is not strictly defined like this. A command, CMD, follows the start of text, STX, or only the start of text, STX, with no end of text, ETX, or command, CMD. For now, we can consider start of text, STX, expectations, LAN attributes types, command, CMD, data, data 0, D0, data 1, D1, and data n, Dn. Next, we will structure the protocol with the checksum, and finally, the end of text, ETX. In the next session, we will try to implement this with Arduino. This time, we tried creating a protocol. As I have explained before, there are no strict rules that say it has to be done exactly this way. You can make slight adjustments based on your preferences, in the parts I describe. Next time, I will try to make the Arduino send data according to the protocol I created. Then, I will see you next time.